So welcome back, and welcome to a new session. What we are going to do now is to introduce a new technicality which we need to program. And again, you will find a Jupyter notebook which has the programming elements which need to be included. So I'm going to take a kind of slightly different route today, in the sense that I will take a top-down approach first. So I'm going to give you the equations you have to program. And then we're going to dig through the basic mathematics, the underlying mathematics. So the topic today rotates around something which is normally called importance sampling in Monte Carlo integration. This is not limited to Monte Carlo integration, but in our case, we are integrating a multidimensional integral. That's essentially what we are doing in a variation Monte Carlo calculation. And that means that we would like to integrate in a smart way. So this smart way means that we are trying to figure out how we can actually save CPU cycles, and when we integrate, to pick points where the function we want to integrate is non-zero. Because if we have many values of the positions which we pick, where the function is zero, we are just accumulating zeros. And that is often a waste of cycles. Now, what we saw last week in connection with the Metropolis algorithm is that we let the random walker just jump around with a fixed step size. This is a kind of a brute force approach, and we often have to tune the step size. And the way this step size is tuned is so that you roughly accept 50% of the moves. There is nothing magic behind that, but that is simply you giving a probability of 50% of accepting the move or not accepting. So that's just like you tossing a coin. That's the deep mathematics behind that simple brute force Monte Carlo sampling. Now, what we are going to do now is actually to use the Metropolis algorithm in its more traditional variant, which is called the Metropolis-Hastings algorithm, which means that we are going to try to guide the random walkers in some way or the other one, which keeps track of the physics which we are interested in. And that's where importance sampling comes in. So what I'm going to give you are actually three different things today. One is a kind of bird's eye view on importance sampling, why this is useful and why we do it. So that's the first element. And then I'm going to give you the equations which we have to program. Thereafter, we are going to look at technicalities with the trial wave functions. And when we are done with these things, we are going to go back and look at the mathematics of the equations which we have to program. So I'm going to take this kind of first practical approach in the sense that I give you the equations, and then hoping that nobody will be too impatient and say, no, I want to see the derivation immediately. But then we're going to go through the derivation afterwards. So I hope you can see the wood for the trees here. So the first thing which we are going to do is actually to not start with importance sampling here in the way we are going to code it, but I wanted to give you a kind of bird's view on importance sampling. And some of you may have seen this if you've taken a course which is called Computational Physics 1. But I just wanted to repeat some of the basic elements, okay? And yeah. So it's essentially very much the same, yeah, that's correct. But you probably haven't seen it in connection with quantum mechanical simulations. So importance sampling is related to the fact, in our case, that we want to integrate in a smarter way. So I wanted to remind some of you of it, and for some of you, you may not have seen this before. Then we are going to go through the basic equations which we are going to use. So we said that last week that the Markov chain Monte Carlo is a way to mimic the physical process of diffusion. And if you take away an external force, the diffusion equation is given by a probability, or probability distribution function, or probability distribution density. And this is normally time dependent. And when equilibrium has been reached, then this probability distribution is time independent, as we saw last week. Now, the standard diffusion equation, the way we derived it from a Markov chain, includes only kinetic energy. So that's the standard way you've seen the physical process of diffusion. So the way we are going to model it is actually to add an external force. So this is actually your particles not only having kinetic energy, but being under the influence of something. So hopefully this is just the influence of a force and not something else. And then we are going to get a set of equations which we are going to include in the calculation. And by solving this equation here, there is actually one possibility to solve them without the external force. And that leads to a standard diffusion equation, which we can solve analytically. And that leads to a transition probability, which is related to what's called a Green's function. Now, for the plane diffusion process, this Green's function will be independent on whether we jump from a state X to a state Y or state Y to X. So it will be the same. That means that in the Metropolis test, we are going to have a transition probability which disappears in the ratios of probabilities. Then we are going to look at an equation which is going to allow us to simulate the way the random walkers jump. And this is a stochastic equation. It's a stochastic differential equation, which for some of you who have taken a course in statistical mechanics, it's called the Langevin equation. So there are actually two elements from statistical mechanics which we will use. And the other one is the so-called, this equation which you see here is normally called the Fokker-Planck equation. So we will go through the derivations of this equation and this equation as well, but we will do that later so that you see the mathematics behind what we are doing. But the whole thing which we want to do, if we now jump back to the whiteboard, and this is where we will stay for some time now. So let me quickly remind you of what we did last week. So last week, we derived the Metropolis algorithm, and the Metropolis algorithm is based on a Markov chain. So let's quickly remind ourselves of the basics of the Metropolis algorithm. So what we have is a Markov chain, and these processes are normally called Markov chain Monte Carlo. And we have a probability Wi at a time t, which is now given by a sum over transitions we can make. So I'm just writing this as a j goes to I, multiplied with a probability which we have at a time t prime. This is the equation for a Markov chain. And this tells you about the likelihood of jumping to a final state, starting from a set of initial possibilities. Now, the way we are going to model this is that we actually have a model for the probability distribution. And in our case, this is the wave function squared. And these j's or i's are going to be the positions of the particles. And then what we need is a model for the transition probability. This is often linked with complicated physics and chemical reactions. And even if we can simulate it, or even if we have an analytical expression, this is often so complicated that it takes ages to simulate from that probability distribution. So the Metropolis algorithm is a way to simulate our lack of willingness to compute a complicated function, or perhaps even better, our lack of knowledge, which is often the more common case. Because normally this, if you have a complicated atom or complicated chemical reactions, it's basically not possible unless you make large simplifications to have a nice analytical expression for this. So the Metropolis algorithm is the one which then gives us a recipe for simulating without knowing this function. And when we let time go to infinity, we are hopefully, if this is a proper stochastic process, we are going to reach the most likely state. So this W becomes time independent. And this is in statistical mechanics and also in fluid mechanics and in other physical processes where diffusion rules the ground. This is normally called the steady state or the stationary state. So I'm taking away the T here just to indicate that this is a time independent state. So this is normally called the most likely state. And we end up then, if we rewrite everything in terms of a matrix equation, we end up then with, or if we just take away the subscript here and let W be a vector, and this W uppercase letter being a matrix, we end up with an eigenvalue problem where we converge to the state which has the largest eigenvalue, which is equal to 1, if W is a stochastic matrix. Now, the Metropolis algorithm is based on us being able to model this transition. So since we don't know it, we can make a model for it. And what we did last time was to rewrite this in terms of a probability of making a transition, T, multiplied with a probability of accepting it. So keep in mind that this is a model which we make. We don't know the expression. So what we have then is an acceptance probability, and we end up with a ratio from what's called detailed balance. So this is a quick repetition from last time. And from detailed balance, what we have is that this acceptance probability, the acceptance of making a move from J to I, divided with making the reverse move, accepting it. This is given by the probability in the new state divided by the probability in the previous state. So this is something we can calculate. Now, the brute force Metropolis assume that either this process of Ti going to J and Tj going to I is reversible, which means that Ti going to J is equal to Tj going to I. Or alternatively, we just put it to 1, assuming that we don't know anything about it. Now, what you see here is actually the final algorithm, is that we then end up with the following algorithm, and this is the Metropolis algorithm of 1, and then the ratio between Wi of Wj of Ti goes to J, and Tj goes to I. Now, what we did last week was simply to assume that this process is reversible, and then we are just left with a ratio between the wave function squared. So in our case, Wi is given by the wave function in a position, the trial wave function, in a position R of I squared divided by the norm. And the norm is just an integral over all the possible positions and with a wave function, and I'm just writing, so this should be an uppercase R of R squared. And this D of R contains now all the positions of all particles. And this R of I is a specific set of positions for all the particles. If you have 10 particles in 3 dimensions, this R of I has 30 components, 3 times 10. 10 particles, and they are X, Y, Z components. So this is the way we model it. And you see now one of the benefits when we do the Metropolis test is that you're taking the ratios of probabilities, and then the norm, which is a difficult integral, which you want to avoid, disappears. For those of you taking a course in statistical mechanics, or if you have taken it, then this probability would then be replaced by, for instance, the Boltzmann distribution. And the Boltzmann distribution has what's called the partition function as the normalization constant. That is also the nasty object. And you know that in statistical mechanics, if you have the partition function, you can calculate all other statistical properties from the partition function. So in statistical mechanics, for a theorist, the holy grail is actually to be able to find the partition function. Now, this is the same as a normalization constant. And that means that if you do statistical mechanics, if you simulate something like an Ising model or some of these spin models, these popular models, then you always end up with ratios between probabilities. And these are ratios which are easy to evaluate normally. So what we want now is a model for these probabilities. And this is going to lead to importance sampling. So what I wanted to give you first is a kind of bird's eye view on importance sampling. So what is importance sampling? And the best way to see that is actually to look at an integral, which we want to calculate. So let's take a bird's eye view on it. So if we now look at an integral I of, suppose now that we simplify the integration limits from 0 to 1, just to give you an example. And then we have a function. This is not limited to that because we can make a change of variables. But this function here is something which we can rewrite if we introduce the uniform distribution. So if you now look at the uniform distribution, and this is normally the standard distribution which is used to generate random numbers computationally. So that's why we often start with an integral like this. So in this case, I just chose the integral from 0 to 1. But what we often do is that we generate a given random number according to a distribution, but all the basic generation of random numbers are done by the uniform distribution. And this uniform distribution, P of x, d of x, when we take the standard one, is given by d of x when we have 0, so x less than 1 and larger and equal to 0. And then we have 0x. Okay? So that means that if you look at that specific integral, since I have this equation here, I can actually rewrite this as the expectation value of the function f of x. And this is the same as p of x, f of x, d of x. So this is also a very important result, that the expectation value of that function represents actually the integral which we are dealing with. So there are two key elements. One is a change of variables. Our integral is often not given by 0 to 1. And two, we want to include importance sampling in order to improve the calculation of this integral. And I will try to motivate why importance sampling is a good trick. And I will show you some simple examples so that you can build up an intuition why this is interesting and why it's useful. So if you now look at the change of variables, which may be relevant in case your probability is an exponential and you have an integral which goes from 0 to infinity. Then, since the random numbers are always generated with a uniform distribution, you would like to make a mapping from the uniform distribution to the exponential distribution. So just keep that in mind, that the basic algorithm for generating random numbers is based on you using the uniform distribution. And then you have to make a mapping. This is something you have to do anyway. So if you now take a very important aspect with these distributions is that in principle, they should obey the fact that P of X of D of X is equal to 1. So they should be normalized. The function should be incrementing. So if I integrate from minus infinity up to a variable X, that number should be smaller if I integrate up to a number X, which is larger than the previous one. So the cumulative distribution is another property which is very important. Another thing which is important to keep in mind is that probabilities are conserved. This means that you cannot find a smart distribution which makes you become a lotto millionaire, period. So the probability of becoming a lotto millionaire is the same. Sorry, guys. There is no way to find a smart distribution which allows you to do that. So the probabilities are conserved. So if I make a change of variables and I have this probability, and then I go to a new one, D of Y, that has to be conserved. So to give you an example, then what we can do, we can integrate this relation, and then we can find X expressed with Y. So that means that I get an X of Y if I integrate up on both sides, and I assume now that X is given by the uniform distribution. So the X variable is the uniform one. Then I have Y, and then I have my P of Y of D of Y. So a typical example, you could now assume that X is the uniform distribution, and P of Y, D of Y is e to the minus Y of dy. And then Y goes from 0 to infinity. Then I want to find the mapping from a uniform distribution to the exponential. So if I plug this in, then I have that X of Y is now given as an integral from 0 to Y of e to minus Y prime dy prime. And this gives me simply, when I integrate, 1 minus e to minus Y. And then what I can find then is that Y of X, if I just invert this relation, I have that Y of X is minus ln 1 minus X. And remember now that X goes from 0 to 1. So you have a random number generator which generates these points, and then you make a mapping. And you see now that if I put X equal to 0, then I have ln of 1, which is 0. So if you now just look at the case when X is 0, that gives us Y equal to 0. And if X is equal to 1, then I have log of 0, and I have a negative number. So that means that then Y goes to infinity. Okay? Because then I have log of 0, then I have the negative log, which means that then I'm getting infinity. Okay? So now I've done a mapping here. So I'm going to show you another example, which now I want to link with importance sampling when you integrate. So you can think of a new probability. So this is not my uniform distribution, but I'm cooking up a probability. Actually, this guy here behaves like a probability. You can use this as a probability for X between 0 and 1. Now I can also show that for this specific distribution, if I do the integral here, this gives me 1. And it has the cumulative properties, which I'm looking after. So it has all the properties of a distribution. Now, what I could do now is to define a new distribution. I can relate this to the uniform distribution. So what I could say now is that I have the uniform distribution for P of Y of D of Y, which is dy. So Y now is also a variable between 0 and 1. And it's given by the uniform distribution. So Y follows the uniform distribution. So I'm just inverting X and Y here. And you will see why I'm doing that. Then I can calculate y as a function of x. And if I do the integral, then I will get that this is equal to 1 divided by 3 of x of 4 minus x here, like that. And then I can change it, and I can find my variable y in terms of x. So that means that I can now, if I take this relation here, I can actually find x in terms of y, which is a uniform distribution. So I can then rewrite it, and then I can find x equal to 2 minus, and then I have 4 minus 3y, or 1 over square root of 1/2 multiplied with 1. And then you see that when y is 0, then I have x equal to 0. And when y is equal to 1, then I have x equal to 1. Why am I doing this? I'm doing this now because there is a special integral I want to calculate. And if I use this new distribution, I'm getting a very interesting result. So let me try to show you the function I want to integrate. So I have the integral, and I'm still staying between 0 and 1 for simplicity. And this is a famous integral, which you probably have seen before. And that gives me pi divided by 4. Okay? Now, I can evaluate this in the brute force way. I can now simply pick random numbers between 0 and 1 by the uniform distribution. The problem with the uniform distribution is that it is not going to give us a good result. But we can actually improve this result. So let's now look at the concept of importance sampling. So what I'm going to say now is that I'm going to rewrite this integral. So this is my integral of f of x of d of x from 0 to 1. Suppose I can rewrite this one by multiplying with a function. So now I'm not assuming that this is a probability. I'm just multiplying with a function. And if I take this f of x of divided by p of x, so I'm assuming that f of x divided by p of x is a number which is non-zero. If I look at this function here, my hope now is the following. So I could obviously say that p of x is now a distribution, is a PDF, probability distribution function. And we could assume that this p of x is equal to this function which I cooked up here. Why is this function so interesting? So if I take p of x to be this one, there are some interesting results here. So if I take the ratio of f of 0 with p of 0, and I take f of 1, I'm putting an equality sign because I'm going to get the same number. So I get the same number at the two endpoints. Now, one thing I could do now is to make a plot of these two functions in the integration domain. So what happens then? So if I make a plot of these two functions from x from 0 to 1, and this is now the two different functions. So I would have now, this is the function I want to integrate. This is my f of x. And then I have the other one that goes also like this. So this is my p of, this is very sketch. I'm just making a sketch of it. But the important thing is that this ratio between f of x of p of x is close to a constant. Why is that interesting then? So let me give you a hint. So when I evaluate an integral stochastically, so if you now go back and we have this equation for the integral, which we are evaluating, and this applies to what we are doing in the project as well. We have a probability distribution, and now let me call this P of y of f of y of d of y. So this is the expectation value. So this is an expectation value of the function f. Now, one thing we want to have together with the expectation value is the standard deviation. The standard deviation is given by the square root of the variance. So that means that we want the variance of this function f. And that is given if we have the probability as a function of p of y, and then I have my f of y squared, d of y, minus, and then I have my p of y, and then f of y, dy squared. This is the expression for the variance. And then the standard deviation is the square root of the variance. So the STD of this function f is just the square root of the variance. So that means that what you would tabulate when you're performing these Monte Carlo calculations is E, the expectation value which you find, plus minus the standard deviation of f. Okay? So when you run a Monte Carlo calculation, the way you have to think of it is like a numerical experiment. So you have something like 1 million samples, and that gives you an expectation value. But when you compute something like this, you have to provide the standard deviation. That is the estimate of your error. So later in this course, we're going to look at what's called resampling methods. So some of you have taken courses in machine learning or statistical analysis. And then you have encountered resampling methods like the bootstrap, cross-validation, blocking, jackknife, etc. Lots of names. And these are all ways to estimate in a reliable way the standard deviation. So that means that when you publish a paper or publish something with a Monte Carlo calculation, if you don't include the standard deviation, you will get everything back. Just come back with the errors. So when you do Monte Carlo calculation, you have a way to estimate the statistical error. Now, if we now go back to what we have, so think of this expression which you have here, right? But now we go back to what we had in the previous slide, and we look at the integral which we have rewritten. So we now have this integral. So the function which I put f of y is given by this one. Then I cooked up a probability distribution here, which follows my function. So that means that this f of x, p of x, is close to a constant. Okay? So if this function here is a constant, what do I get as variance? So suppose now f is a constant. What do I get as variance? You get 0, right? So, and this is what we want. We want an error which is as small as possible. So what we are searching for when we run a Monte Carlo calculation is a distribution which follows the function we want to integrate. And this is what Monte Carlo with importance sampling is going to do for us when we now are going to bake in a model for the transition probability. Instead of letting our random walker just jump randomly in space with a step which we tune. Now we're going to make this jumping in a more intelligent way. So the thing with the importance sampling is then that what we can do then, if we look at this integral, if this particular example which we had with the simplified expression, so we start with something which looks like this. Suppose we have this, I'm still doing this example. I rewrite it as a P of X, and then we have F of X. So I just found a probability distribution, this function P of X, which I have. And then I made a transformation. And here I have my uniform distribution, which is dy, and probabilities are conserved. So I have P of X, d of X. Then that means that my P of X function is actually equal to dy dx. And then I can change my integral to an integral over y. So in principle here, I should change the integration limits, but the integration limits are the same in this case. But in general, the integration limits change when I make a change of variables. But in this case, I have defined x and y to be between 0 and 1. So there's no need to change the integration limits. So what I get then is an integral where I now evaluate x. I call a random number generator, a uniform distribution for y. I make the mapping to this x, and then I have to calculate now this integral of dy. And since f of x divided by p of x is close to a constant, my hope now is that the standard deviation becomes much smaller. Okay, so this is roughly the overarching philosophy. And now let me just bring back some slides where we have a simple example of a calculation with that distribution. So what you see here, this is just a plot of these two functions. So I have my two functions. The first function is actually, I have defined it here. This is the probability P of X, which I show you. And this is my function I want to integrate. And then I simply make a plot. So this is my integrand, and this is the new integrand. So when I take the ratio between the two, and you see that this stays as a constant ratio here. If I then look at the results I get when I integrate, what you have here is now the CR stands for crude Monte Carlo. This is the number of Monte Carlo cycles. And you see now that if I just pick a uniform distribution, then my result, even if I put in millions of cycles, my result doesn't improve that much. And you see also that what I'm getting now is a standard deviation here, which just moves towards a constant, which is just the evaluation of that specific integral. Now, when I now do importance sampling, you see that the result is getting better. So this is the integral multiplied with 4. So my integral should be pi divided by 4. If I multiply with 4, I should get pi. And you see also that the error, this is my standard deviation, is now 2 orders of magnitude smaller. So in Monte Carlo calculations, what you want is to have a sampling which is more intelligent. And this is what importance sampling gives you. So let's go back a little bit to the whiteboard again. So suppose now that we, in our calculations, we have just one particle. And the wave function is just given by a Gaussian. It could be a harmonic oscillator in the ground state, like we're having in the first project here. So if you then look at your wave function in one dimension, and you square the wave function, it would look like a Gaussian here, something like this. So we can just write P of X here, because the wave function squared is the probability divided with a normalization constant. So when we do the brute force sampling, so we pick a position first. So this would be a position, and let's call this xj. And then we are making a transition from xj to a new state. So this goes to an x of I. So this x of I is something which we will rewrite as an x of j plus some step size, which I call for delta, multiplied by a random number with a uniform distribution. So this is something which we call a step size, and we often tune this one. And then we generate a random number between 0 and 1. But then what we do then is to subtract 0.5. So R follows a uniform distribution, and it gives a number between 0 and 1. And you see now that if I produce something which is less than a half, then I get a negative number, which I want because I want negative values of X also. I don't want only positive values, because then if I were to have positive values, I would just stay here. So this allows me to make a jump. But you see now that what I'm doing is I need to tune this one so that I don't end up jumping here or here many times. Because then when I'm integrating, I would just include lots of zeros, and you want to avoid that. So one recipe is actually to tune this one so that you accept roughly some 50% roughly. That is just you tossing a coin of 50% being inside here and 50% being outside. There's nothing deeper than that. So you can often tune this one to just accept 50% of the moves. Okay? That sound reasonable? So, and this is what we will do in the beginning. So that means that we can move to an xi here. So that could be the next one. And the Metropolis algorithm tells us that we accept immediately moves to higher probability. But we also want to move out again. So we could now have a new step where we move here. So this could be an x of L. And then we would have this probability. This will still be non-zero. Now, important sampling means that we are going to make a sampling where we avoid this kind of ad hoc rule, where we simply say that we accept 50% of the moves, we tune this quantity, but now we are going to have a random walker which follows the distribution of the function. And this is where this Fokker-Planck equation comes in, because we are going to get a probability distribution or a transition probability which will be proportional to the trial wave function. So that means that the way we jump is then conditioned by this shape of the trial wave function. Okay? So this is the kind of overarching motivation why we do importance sampling. Then what follows is a lot of technicalities. So I just wanted to give you this kind of overarching picture first, so that you see roughly why we do what we do. The rest are just calculational details. Any questions so far? So there's another thing which I wanted to say something about, which we skipped a little bit in the previous weeks. And this is, how do we make the trial wave function? And this becomes a little bit important for us, because we are going to make a trial wave function which is not only this given by the single particle energies. We are doing this now when we build up the project, because we have analytical answers to the energy with the harmonic oscillator. But at the end, we are not interested in non-interacting systems. They are boring. We know what they look like. We want the interacting stuff. We want real life. And then we have to make a model for the wave function. So let me show you how we can make a model for the wave function without or with a minimal insight about the physics. So I'm going to present some technicalities which we need to think of when we are going to write the program for the trial wave function of psi of t. So one of the things which is pretty simple to look at is, so we can actually guess the form of the trial wave function by looking at the local energy. So we are integrating a quantity which we have defined as a local energy. And this is a quantity we have defined in terms of an R. We have a trial wave function, psi of t of R, and H is a Hamiltonian, which then acts on this trial wave function. This is the quantity we are integrating. Now, let me look at an example, a simple example. So this is the electron in hydrogen. So by just looking at this equation, we can guess a form of the solution, which for this hydrogen atom is pretty close to the analytical answer. So the point now is, can we, based on the Hamiltonian, extract some minimal physics which has to be there, without us just guessing widely? So if you look at the Hamiltonian here, we would have a trial wave function, psi of t of r, and then we have minus, and this is in scale units where I put the mass equal to 1, h bar equal to 1, etc. And then we have the derivative, the spatial derivative, minus c divided by r. So this is a number 2, actually, times psi of t. So this is just the distance between the electron and the atomic nucleus. And this is a scalar, r. So when you don't see the vector sign, is a scalar. Now, what is common to do is to transform this equation into spherical coordinates. And this is what we'll do after the break. And what we will show then is that the wave function psi of t, this trial wave function, t stands for trial, is going to have a component which goes like e to the minus r, which is part of the analytical solution for the hydrogen atom. And this is something we will do after the break, if that is okay, because I've seen I've gone 2 minutes over time here. Any questions so far? Okay, so let's take a break and just stretch legs and be back in 15 minutes. Feel free to ask questions if you want. So I wanted to bring up this element with the way we generate an ansatz for the trial wave function. And then we are going to go back to the codes and see how we bake in that element. Another thing which I wanted you to just keep in mind is that in the lecture notes, in the Jupyter notebooks, I have tried to make pretty simple codes, which just illustrate how you can transfer from a trial wave function and perform the integration. Now, the framework which we have in C++ and in Python is actually a little bit more advanced, so it contains object orientation and more advanced programming. But you can start, when you write the programs, just take a look at the simpler programs which I have here, because they are tailored to 2 electrons in a harmonic oscillator trap, but these electrons are also interacting, which means that the wave function is a little bit more complicated. And I wanted to say something about the wave functions, and then we are going to look at the technicalities of importance sampling. And then I'm going to give you the equations, and I'm going to state them. This is not the nicest way of doing things, but then, so I'm going to throw you into deep waters, but then hopefully I can bring you back again, where we just step through the mathematics behind the equations. So today serves more as giving you the kind of overarching picture of the kind of methods we need to program. So the thing which I wanted to say a little bit is, where do we find these trial wave functions? And how can we, without knowing what the solution should be, have at least some minimal requirements about the form of the wave function? Now, if you look at the electron in the hydrogen, for the hydrogen atom, what is normally done here is that this equation is rewritten. Yeah. Okay, so the way you normally solve these equations analytically is to rewrite them in terms of spherical coordinates. And if you then look at the radial wave function only, so if we take this equation and take the radial equation, because there is a problem with the equation which you see here. And the problem deals with the fact that when R goes to 0, you have a divergence. Now we know that the energy doesn't diverge. The hydrogen atom has a finite energy. So that means that there must be some magic in here which cancels the divergence. So if we look at the radial equation, remember you can, when you change to spherical coordinates, you will have equations for the two angles and then for the radius. The two angles don't cause any problems. The problem is in the divergence you get in R. So the radial equation, when we do that, that leads to the following. That leads to a local energy. This is the radial component. So I'm just putting a little r here. Sorry, not little r. I actually used an uppercase letter. So this is just the scalar. It's just the absolute value of the distance between the electron and the atomic nucleus. And this is now given by the radial part of the wave function and taking away the angular part. And this contains now minus 1/2. And then there's a derivative of d of r. And then we have minus 1 over r, d dr, minus z over r. And this is multiplied with this r of t. And then there are some additional terms, which I'm just leaving out. These are just finite terms. I'm just singling out these pieces here because they are the important ones. Now, if we now look at what we have, when we look at quantum mechanics, we have that in the limit of r goes to 0, we know that this quantity here is assumed to be finite. So this is given by a number m, which is smaller than infinity. This is a basic assumption we set up when we are looking at the solution in Hilbert spaces. And this belongs to what's normally called the L² type of wave functions or solutions. So this is a basic assumption we are making. So we know that the total kinetic energy should be constant or should be finite. So this is an important assumption. So that means that when I now look at in that equation, when I have d of r of t of d r squared and d of rt of d of r, they should be finite. Now, finite when r goes to 0. So if I look back to the equation which I had, you see now that what happens when r is going to 0 is that the term which you see here is going to go towards a constant. This term is going to be a constant. Then there's going to be a 1 over r here, which needs to cancel that piece. So when I take the limit of r goes to 0, the terms of interest, the terms which need to cancel each other, are actually the terms with r of t of r. And then I have this minus 1 over r d dr minus z over r times r of t. The rest of the terms are terms which are irrelevant for this case because they're just going to be finite numbers. And the two divergences which I have are the two 1 over r terms. Now, there is an interesting thing here which you can deduce from this. If you look at the equation which you have here, this is in 3 dimensions. In 2 dimensions, you have a similar equation with a 1 over r. What happens in 1 dimension if I take this second derivative? what do I get in one dimension for a Schrödinger type problem with a Coulomb interaction? So I will have in 2 and 3 and higher dimensions, I will have a term 1 over r here, always. When I make a transformation to either polar coordinates or spherical coordinates or higher order types of coordinates in higher dimensions, there will always be a term like 1 over r. What happens in 1 dimension? Will I have a term like this in 1 dimension? No. This has a very important consequence. That is the reason why you don't have a solution analytically for the Coulomb problem in 1 dimension, because there is no term in kinetic energy which cancels this divergence. So a Coulomb problem in 1 dimension doesn't have an analytical solution. The way you would do it is to cheat, and you would typically add what's normally called a screening constant. So you would have an r plus some delta, some finite quantity. Then you can solve the equations. So if you now look at the equations which you have here, what we want is actually to have these 2 divergences to cancel each other. So if you take this equation here and we just rewrite it, you take these 2 equations, no, these 2 terms, and just rewrite it, what we get then is simply 1 over RT, and then we have d of RT of d of r is equal to minus z. And this is something we can solve, right? So that simply means that I have r of t of r is equal to E minus Z times R. So if you go back to the analytical solution of the hydrogen atom, you will see that the analytical solution contains a term like that. And then it is a little bit more complicated because it contains a product of so-called Legendre polynomials. No, sorry, not Legendre, Laguerre polynomials. So the total analytical solution contains this factor here multiplied with some polynomials, which are the Laguerre polynomials. But this way here, by just looking at the Hamiltonian, is a way by which we can say something about what the wave function should look like. So what we can do next, and this is one of the things we did in one of the examples last week, is that we replace this C with a variational parameter. And we just put a parameter alpha, and then we calculate the energy, and we vary the energy as a function of alpha. So if I'm having an atomic physics problem, I could now make an assumption for, let's say, neutral helium, which contains now just 2 such functions, one for electron 1 and one for electron 2. You also see that if the potential is not attractive, if I have a plus sign here, then this will have a plus sign here. You can repeat the same exercise for 2 particles which repel each other with a Coulomb type of interaction. But then you have to rewrite this function here in terms of the relative distance and the central mass distance. Now, the relative distance can go to 0 when 2 particles are just getting closer and closer to each other. So for the relative distance, then you will have a divergence when the 2 particles are getting very close. And the equation you will get is similar to this one. So that means that if I now look at, I'm just going to give you, you will find more of it in the notes, but if I have 2 particles, which interact through something like a Coulomb interaction, through a force which goes like R12, there's 1, 2 here, and where R12 is the relative distance between particle 1 and particle 2, then you can show, if this is an attractive force, then you can show that this radial part RT of R12 is proportional to E to the power of some parameter beta multiplied with R12. That will be a minimal requirement for an interacting system of two particles. So if you now have, let's say, two particles in atomic helium, then you could make an ansatz for the total wave function for the ground state. For ground state, so you could think of this as atomic helium. Of atomic helium. We could now think of a total wave function for two particles, R1 and R2. That could be given by some variational parameter, e to the minus alpha, and then I have an R1. This is the absolute value. This would be the single particle piece. And then I have an e, I can have the same parameter of R2. So same variational parameter for the single particle piece. So if there is no interaction, actually the ground state will be proportional to this, if it's a non-interacting system. But then I'm going to replace that one. Since I have an interaction now, I could write it like a B beta with a new parameter of R12. That could be an ansatz where, one, I cancel the divergency when electron 1 is getting close to the atomic nucleus. Same with electron 2. And in case electron 1 and 2 are getting close to each other, the divergence I would get in the Coulomb interaction is then cancelled by a term like this from the kinetic energy. So this form of the wave function which you have here, this ansatz which you make, is information which you extract just from the Hamiltonian itself. And you're requiring that the energy should not diverge. And then you have two divergences which have to cancel each other then. So this is one way we can actually make an ansatz for the trial wave function. Now, the examples you will find in the Jupyter notebooks, they are tailored to two electrons in 2 or 3 dimensions, but they are not moving in an atomic nucleus, around an atomic nucleus, but they are trapped by a harmonic oscillator potential. So the example which I have in the Jupyter notebooks, so example codes, which you will see again and again. So this is a system I'm looking at. So I have an harmonic oscillator in 1, 2, or 3 dimensions. And then I'm assuming that the 2 electrons are in the lowest lying state. One will spin up and spin down. Since these are filling the same harmonic oscillator state, so that means that this is electron 1 if I'm in 1 dimension. So this is electron 1 quantum number, electron 2 quantum numbers is equal to 0. Then my single particle wave function is just given by the product of 2 harmonic oscillator functions. So that means that in this specific case, I have a trial wave function, and now I'm writing this in terms of vectors, but they can be given for 1-dimensional, 2-dimensional, 3-dimensional. So I would then have a mean e to the minus alpha. This is a variational parameter. And then I have R1 squared plus R2 squared. And this is something which I will call for psi OB. And I will tell you what psi OB is. So OB stands for one body. So that is the single particle piece. So this is one body. But then I can add an interaction piece. And this interaction piece has something which runs like an exponential with an R12. In general, this will be a little bit more complicated. It will represent many other particles. So this is normally called the correlation or the interaction piece. So I will often write this as a psi of C, and with two particles, it's just R1, 2 here. It's also called the Hjorth factor. After Hjorth, who did groundbreaking work in electromagnetism, by the way, and got the Nobel Prize for that, Hjorth actually postulated this as a trial wave function. So this is the minimal kind of requirements we have from the physics of the Hamiltonian. Then you can make more complicated models, and you can bake in more insights if you want. So what is pretty common for this type of system, which we have, is a correlation function. So in the examples, what I have done is to assume that this trial wave function is now given by a harmonic oscillator, which has a variational parameter, R1 squared plus R2 squared. And then it's multiplied with a function which goes like e to the power of a of Ri12 of 1 plus beta R12. This is a slightly more complicated function, and you will often see that this function here in a more general form you will often see that as an exponential, and then you can have a sum, and we are dealing with the more particles. So we have a particle I and particle j, and this can be to the power of k. And then there is a parameter beta of k that becomes a variational parameter, which you can tune. And then there is a denominator, which is often, and the way these forms look like is just to avoid that you have this divergency at Rij going to 0. And then you will have a new set of parameters, an alpha of L. And then I have this Rij to the power of L. And clearly, the more terms you include, the more parameters you have. So in our case, alpha L and beta k are variational parameters. Now, the one body part is the simple piece to include in the calculations. The one which causes problems for us is actually the Hjorth factor here, especially when we have to calculate the second derivative. Because when we now want the local energy, for the calculation of the local energy, we need the second derivative of this part. And the second derivative of this part is actually the sum of the second derivative for particle 1 and for particle 2. So if we only have this piece, which is what we will use in the beginning, then life is pretty simple. However, when you're writing the code, at a certain point, we also have to include the derivative of that one. So if you're using automatic differentiation and you look at the Python framework which we have, that includes the possibility to use automatic differentiation to calculate these derivatives. Because when you make this trial wave function more and more complicated, to calculate the derivative by hand is very error prone. Because you see now you're going to deal with two indices, and this is not the particle 1 plus particle 2, but it's actually the square root of the distance between particle 1 and 2 squared, which makes calculations of derivatives, I mean, you can still do it, but it's a little bit boring because it's so easy to make errors. So in the lecture notes, you will find the technicalities for setting it up without using, let's say, automatic differentiation. So I'm going to discuss a little bit these technicalities because there are some important aspects. So one technical aspect deals with the calculation of the Metropolis test. Because in the Metropolis test, we are taking ratios of wave functions. And if you just move, suppose now you only have this part of the wave function. So when you're dealing with a Metropolis test, then you are taking the position of part, if you move one particle at a time, so small technicality. In the Metropolis test, in Metropolis, and you will see now why we move one particle at a time. With the one body only, psi OB only. So if I'm moving one particle, there's no problem. But if I'm moving two particles, what I'm having then, if I have the harmonic oscillator, so what I will have then would be e to the minus alpha, and then I'm squaring this quantity, so that means that I get a factor of 2, but let's just leave that factor of 2 out. So I would have R1 squared, and I'm putting a prime here because this is a new position. So if I pick particle 1 only and I move that, then what I need to evaluate, as you can see here, is just particle 1, because particle 2 stays in the same position. So when you're moving particles and you're taking the Metropolis test, you can move all particles and perform the Metropolis test, or you can move one at a time. If you move one at a time, you can actually save CPU cycles. So this particular case gives us 1 e to the minus alpha, and then I have R1 prime, the new position, divided by e to the minus alpha R1 squared. Obviously, you would never compute it like this because that means a calculation of 2 exponentials. You would simply calculate this one as e to the minus alpha, and then you have R1 squared minus R1 squared, right? So this is just a technicality which you should start thinking of when you're implementing things, because this will speed up your code. So it's common, as for those of you who did the easing model, so how many of you have calculated the easing model? 1, 2, 3. And you remember then that in the standard Metropolis, you would flip one spin at a time. So you flipped one spin and you did the Metropolis test. The reason for that is that that simplifies the ratio in the Metropolis test. So calculating the change for one particle at a time, so you would have a loop where you move just one particle, and then you move obviously all particles. So you can decide whether you want to move all and perform the Metropolis test and think of that as a new position, or move one at a time. So moving one at a time means that you can simplify many of the calculations. And that saves CPU cycles. But let's go a little bit back to the Jupyter Notebook, because now I wanted to show you so that you can get started with the coding pretty quickly. So let's just go back to the Jupyter Notebook for the rest of the lecture here. So if we go back, so let's just scroll through, come back to this one a little bit later. Now what I have here is a simple code which implements importance sampling. And I'm going back to the equations. And then next week, we are going to go through the mathematics of importance sampling. Now, as you can see here, I have coded this specific trial wave function, which now includes this correlation part. But the plain harmonic oscillator coordinate is given by these two guys, this one for particle 1 and this for particle 2. Then I calculate the relative distance. So in project 1, when you begin, you don't need to evaluate that part. You can leave that out, because we are not going to put in the interaction first. We are going to make all the tests and developments without the interaction between the particles. That means that your trial wave function will simply be given by this piece till here, period. So then I have another function which you need to code. So in the framework, we have tried to make it object-oriented. But when you're now developing your codes, just to baby step yourself through some simple things, just do this for 1 and 2 particles in 1, 2, and 3 dimensions. Just a plain harmonic oscillator problem. And then you have a local energy, which is much simpler. So here, I've actually calculated the local energy with this correlation piece because I'm doing the full case for these 2 electrons. And then I have this term in addition, which is given by these terms here. But if I leave out and just have a plain harmonic oscillator, then my local energy contains this part here, plus this term here, which comes from the harmonic oscillator potential. The rest here, which you see, is the derivative of that more complicated part of the wave function. Then I'm defining the quantum force, which I'm coming back to now, which deals with importance sampling. So what you will find then is the position old new. We loop over this variation of parameters. And in this particular case, I'm actually now looping, as you can see here. So I do a loop over particles. So I move all particles. So this is not the smartest way of doing it from efficiency. So this is often, the programs here are more from a pedagogical point of view. Now I'm moving all particles. But when you are thinking of writing your own code, you should think of moving 1 particle at a time. And it's useful to time it and see if you actually increase speed when you just move 1 particle at a time. And we have the Metropolis test. I calculate the energy squared. And this specific case here gives me something like this. So this includes importance sampling. So let me now throw at you the equations for importance sampling. And then hopefully next week, I will bring you back on shore so that we know exactly what is going on. So what we want to do is, so I'm still on this overarching level. What we want to do is to find a way to jump in space in a smarter way where we keep information about the trial wave function. So here we get inspired by fluid mechanics and the Fokker-Planck equation. So the Fokker-Planck equation is something you can derive where you then have the standard diffusion term, which is the kinetic energy. So the first term you see on the right-hand side is the kinetic energy term. The second term is you moving in a force under the influence of a specific force. So this could be particles which are under the process of diffusion, but under the influence of a gravitational field. So F would then represent the gravitational force, just to give you an example. And then what you are doing then is that you have a probability distribution, which when you simulate long enough, should reach the most likely state. That is your stationary state. And that means that the probability distribution becomes time independent. So probably so how many of you have simulated in a course in numerical differential equations, the diffusion equation? Only 1 of you. Okay, 2. So there is a simple example. So you could think of, just let me give you an example here. You could have an initial condition at t equal to 0. And this could look like this, t of x. So this is a function of x. Yeah. Oh, sorry. Yeah, let me bring up the. So just to allow you to build up some intuition. So you could think of your initial condition, which looks like this. So we could now have 0 to 1. So this could be the temperature of the temperature distribution of a rod, right? So you have a rod with a given temperature, and you could assume that it's cold in the 2 ends. and then it has an internal temperature. This is just one of many, many examples. And you probably have heard about Fourier's law, where you actually look at how temperature changes over time. So if I put this, if you now think of this as the temperature distribution in a rod, and you have the two endpoints, which have temperature 0. And then there is some temperature inside. So, or a given temperature. This can just be scaled. So this could be room temperature, the two endpoints, and then somewhat warmer inside. So what happens after some time, if I put this rod in a big lake, what should this distribution look like? At a given time, many, many, many minutes or hours afterwards. What should it look like? Yeah? Say it again. Yeah. How would you expect that this one moves? Yeah. So what you would get then is that equilibrium, you reach equilibrium, and then it should have the same temperature everywhere. So what you would see then when T becomes very large, when T goes to infinity, then your temperature distribution, because then you have reached the most likely state, then your temperature distribution should look like this, just flat, right? Does that sound reasonable? So this is normally what we say as Denmark seen from the sea. No, nobody understood that joke. The Danes call Norwegians for the mountain monkeys. So this is what you normally call, oh, this would be the Netherlands seen from the sea. No, no, we don't see the Netherlands from the sea because it's below sea level. Actually, the Dutch people are the tallest people in the world. Did you know that? And there's a funny thing, a fun fact. In the US, in the state of Michigan, in the western parts, there is a huge Dutch part of the population. So many people settled there in the 18th century. And they are the tallest people in the US still. Okay. That was just one of my many lame jokes, guys. Eh? Okay, let's go back a little bit to the Jupyter notebook. So what we are going to do is actually to simulate, with this equation, we get a minimal form of the so-called force here. And we are going also to simulate this equation here, which is called the Langevin equation. And next time, I'm going to give you a link between the Fokker-Planck equation and the Langevin equation. So these are two technical aspects which we are going to implement. So this Langevin equation is the way we now simulate the next position. So this D, if we now think of this as kinetic energy, this D is h bar squared divided by 2 times the mass of the particle. So we are going to run this with a natural unit. So we'll put the mass equal to 1, h bar equal to 1. So in our case, D is going to be 1/2. Because this mimics, so we don't have the standard diffusion parameter, which you would extract from experiment, but we are going to simulate the movement of quantum mechanical objects, and then this D will just be given by 1/2. This is a stochastic equation where we now have something which moves under an influence of a force, which takes care of the long-range behavior. And then we have some random fluctuation which are instantaneous. This is a stochastic equation you can integrate up using Euler's method. So you would get x plus a d times f. This is a derivative now term, and this is a delta t, and then there is some stochastic term here, which is normally assumed to be a Gaussian variable. So this is the way we are going to implement the jumping in space. So instead of having y equal x plus a step, which we tune, we now have a movement which follows this object f. Now, what you can do then is to assume that you have isotropic diffusion, and we have this time-dependent probability density, and where this f is the component of the drift term or drift velocity, which is caused by some kind of external potential. Now, the convergence to a stationary probability can be obtained by setting the left-hand side to 0. So this is the steady state requirement. So dp dt becomes 0 because you get a probability which is time independent. And that means that the only way you can fulfill that one is to have this relation here being fulfilled and equal to 0. That puts a condition on the form of this f. So this f, when you do the algebra here, and I invite you to do that as a small exercise, you can actually find that this f is proportional to the wave function, the trial wave function you have. So this is the way we are now going to implement the solution to the problem to find the way we're going to make the transition. So this f now is now given in order for these equations to be fulfilled, to this to be equal to 0, which you have here. Then there is a mathematical requirement in our case where the probability is given by the wave function square. So for us, p is the wave function square. And using that, we end up with this requirement. Now, this leads, if we put this in again, and this is something we will discuss in more detail next week. So when we put this back into the Fokker-Planck equation, we can actually solve it analytically, and we can get this solution here. And so I told you that I'm going to throw these equations at you because we need to program them and get started. And then we will step back next week and go through some of the mathematics behind the derivations. So I hope you can, live with this kind of, top-down approach where you get the equations, we're going to program them, and then we can retrace our steps back and then derive the equations. So the way we are going to simulate this transition probability, which is something we don't know, is by this Green's function, which is the solution to the Fokker-Planck equation. The Green's function represents actually a probability. It represents a probability of jumping from x to y in a time step delta t. So this mimics, or this is meant to represent the type of transition probabilities which we want to bake in as information to the random walkers which jump in space. So that means that we need to calculate, when we now look at the Metropolis algorithm, we need to calculate this ratio here, which is different from the one we had before, where we had the wave function squared in a new position divided with the one in the previous one. Now we need to plug in this T matrix, or this transition probability, from going from x to y and from y to x. Now, if I don't have this quantum force, then the solution of the problem, if we go back, so if you put this f to 0, then you can actually find the Green's function for the plane diffusion process. And the Green's function for the plane diffusion process is given by minus y minus x squared. So if I take away this quantum force, what would happen with this ratio here? What happens with g x to y and divided by g to y to x if I take away the quantum force F? Does anyone see that immediately?
It's the same.
It's the same. And then we are back to what we call the brute force metropolis. Because then it's equally likely to go from X to Y than from Y to X. And then these two cancel each other. And we are left with the same ratio which we had before. So adding this quantum force here means that we have this so-called drift term. In our case, from the Fokker-Planck equation, which is here, and with the P given by the wave function squared, we can then show that this F has to be proportional to the wave function. So you see now that there is an additional complication. We need the Laplacian and we need the gradient of the quantum of the wave function. And when we have this more complicated interacting piece, then these gradients become nasty to calculate and error prone. But we will still stay with just a plain harmonic oscillator, which means that the calculation of the gradients are pretty simple. The program which I have here, and just take a look at it, we will come back to this next week as well. This is now a program where I calculate this quantum force using the equation which you saw. And then in my ratio now, in the Metropolis test, I'm actually calculating the quantum force in the old position, as you see here, and the quantum force in the new position. And then you can see now that the Green's function is a ratio between exponentials. So I don't calculate the exponential for the numerator or the denominator, but I actually calculate the ratio and then do the exponential, which you see here. Because calculating two exponentials becomes more time consuming. So these are the things which we need to include. And when we have these ingredients in, so you can take one approach now, okay, I accept the equations and I'm going to program them. And then we just wait till next time and discuss the underlying mathematics behind them. So this is a kind of practical approach we're going to take just to get started with what we want to do. So when you have this part of the code, then we have a good fraction of what we need to establish. What comes after are resampling techniques to calculate better standard deviations. And then we are going to look into Monte Carlo parallelization, which is also important for this type of calculations, because the more samples we can compute, the better it is. Monte Carlo calculations of this type are trivial to parallelize because you can just set up independent processes where you sample individual random numbers, and then you just collect everything at the end. So in previous days, this was called something in a nasty way, actually. We're not using these wordings anymore. It's what's called a master-slave process. So you had a master node, and then you had all the slave nodes, which did the work for you. And then the master node collected data at the end. So you will, if you go into old textbooks on parallelization, you will find that kind of wordings. I have to confess, I've never liked to use it, and I'm not going to use it. But if you go in different textbooks, you will find this kind of wording. Okay. So this is the kind of, I wanted to give you a more kind of bird's eye view on things. And then we are going to look in gradually to go through the mathematics behind these equations. Any questions to what we are going to do here? Okay, so if there are no questions, I'm going to stop the recording. And then we just keep working on the projects. And we have the lab sessions. And if you, when it comes to coding, if you haven't started properly, it can actually be a good idea to just look at the examples I have and don't think of object orientation in the beginning. Just have something which functions and then get started. And then we can keep adding things so that it becomes more like a professional numerical project. So how many of you have actually set up groups to collaborate? Okay, so feel free to talk with the other ones and try to team up. It eases everything a lot.